This video is meant to help you understand the process of conservation of energy and how we can use conservation of energy to help us solve problems. So let's take a step back for a minute and look at the concept of conservation of energy. We know that objects can have either potential energy or kinetic energy, and that we call the sum of those two energies mechanical energy. So let's think about a ball that's being placed at the top of a ramp. All right, you can see the ramp. Here's the ball. What kind of energy does this ball have? Well, it's at the top of the ramp, so it has potential energy because it has the potential to roll down the hill. We haven't let go of it yet, so it has no kinetic energy. And because it has some potential energy, it also has mechanical energy. If you think about the three boxes shown in the diagram as buckets, we would say the potential energy bucket is full. It's all potential energy at this point. The kinetic energy bucket is empty. That's what the zero is there to remind us. The mechanical energy bucket is the potential energy bucket plus the kinetic energy bucket, so this one is also full. Okay? Now, what happens to the ball as it rolls down the hill? Well, let's suppose it gets about halfway down the hill. Here it is. It's rolled down the hill. As it gets closer to the ground, it has less potential energy, so the potential energy bucket is no longer full. It's moving faster than it was at the top, so it has some kinetic energy where it didn't used to have any. But if we look at the potential plus kinetic energy bucket, the mechanical energy is still full. The mechanical energy is the same amount that it started with at the top. That's what it means to say energy is conserved. The total mechanical energy of the ball as it rolls down the hill stays constant. All right, let's look at one more spot. This time let's look at the ball right at the bottom of the hill. Now it has no height, so the potential energy bucket is empty because there's no potential energy. It's moving very fast at this point. In fact, it's all kinetic energy at this point. And we know it's all kinetic energy because ME has to stay the same. The total mechanical energy can't change. So here it's all kinetic. Now what we would say is happening as the ball rolls down the hill is that all the potential energy that it started with at the top eventually gets transformed into kinetic energy when it reaches the bottom. We can see from the middle picture that this doesn't happen all at once, and in fact it happens gradually. So as the ball rolls down the hill, potential energy is transformed into kinetic energy, but the total mechanical energy of the ball stays constant. So there it is. As it rolls down the hill, PE gradually transforms into KE. That's a quick review of conservation of energy as a concept. Now we want to look at this mathematically. So we're going to look at a similar problem, a ball rolling down a ramp, but this time we're going to ask, how can we put numbers to this problem? So here we go. A 0.5 kilogram ball is released from rest at the top of a 1.5 meter high ramp. Determine the speed of the ball when it is 0.5 meters above the ground. All right, the first thing we want to do whenever we have a word problem like this is draw ourselves some kind of picture so that we can take the important information from the problem and transfer it to the picture, and that'll help us organize what we know. All right, so here's our ramp. Here's our ball at the top. The problem tells us it has a mass of 0.5 kilograms, so that's shown here on the ramp. The ball is at a height of 1.5 meters, that's this H right here, and it's released from rest. From rest means it's not moving, so its speed at the top of the hill is 0. All right? That's everything we know about the top of the hill. Now, we also want to know something about the ball someplace else. The problem tells us we want to know something about the ball when it's 0.5 meters above the ground. So here's the ball later on when it's 0.5 meters above the ground. We know its height. We don't know its speed. Now, how can we take this information, apply the rules of conservation of energy, and come up with a solution to the speed of the ball at the bottom of the hill? All right. Well, it turns out this is really pretty easy. There's a three-step process that we can follow whenever we decide conservation of energy is the way we want to go. So here we go. The first step is to calculate the mechanical energy at a place where we know H and V. That's what we would call our initial location in this problem. At the top of the ramp, we know the height is 1.5 meters and the speed is 0. So at that point, we can calculate the mechanical energy of the ball. Step 2 says write an expression for mechanical energy where H or V is unknown. That's going to be down here when we're 0.5 meters above the ground. We know the height, but we don't know the speed. And then step 3, this is what conservation of energy is all about. Set the mechanical energy that we calculated at the top of the hill equal to the mechanical energy that we calculated near the bottom, and we should be able to solve for whatever it is that we don't know. All right? So let's go through that one more time. Find a place in the problem where you know height and speed and calculate the total mechanical energy of your object. Write an expression for the total mechanical energy at some other place in the problem where either the height or the speed is not known, and then set those two mechanical energies equal to each other, and you should be able to solve for your unknown height or speed. Here's what it looks like for this problem. Same ramp, same ball at the top, 1.5 meters high, no speed. Later on, it's going to be 0.5 meters high, and we want to know its speed. Step 1, calculate the mechanical energy where we know H and V. Here's what step 1 looks like. Mechanical energy at the top of the hill is equal to the PE of the ball plus its KE. PE is calculated as mgh. KE is calculated as 1/2 mv squared. So I add those things together. Now I substitute the numbers I know from the problem. The mass of my ball for mgh mass is 0.5 kilograms. Near the Earth, G has a value of 9.8 meters per second squared. And in this problem, the height of the ball at the top of the ramp is 1.5 meters. Plus the kinetic energy, half the mass, 0.5 kilograms. The speed at the top of the hill is 0. So when I square all this, I get 0 times 0.25, which is still 0. Only the potential energy is calculated. And if I multiply 0.5 times 9.8 times 1.5, I end up with 7.35 joules for my mechanical energy of the ball at the top of the hill. All right, step 2. Write an expression for the mechanical energy at some other place in the problem where we don't know everything. So in this problem, near the bottom of the hill, we know the height but not the speed. So we're going to calculate the mechanical energy near the bottom of the hill. Again, it's PE plus KE, mgh plus 1/2 mv squared. I substitute my values. For PE, it's 0.5 kilograms times 9.8 for G. I have a height of 0.5 also, plus 1/2 the mass, 0.5 times V squared. V is my variable in this problem. V is what I want to know. So that just kind of stays and carries along. I multiply 0.5 times 9.8 times 0.5. I end up with 2.45 joules for my PE, plus half of 0.5 is 0.25 V squared. So the expression for my ME, my mechanical energy at the bottom of the ramp, is 2.45 plus 0.25 V squared. All right, now energy is conserved. So the mechanical energy that I calculated at the top of the hill, 7.35 joules, has to equal the mechanical energy that I calculated near the bottom, 2.45 plus 0.25 V squared. Step 3 says force them to be equal. So we make the ME at the top equal to ME near the bottom. I make my substitution. 7.35 equals 2.45 plus 0.25 v squared. And now it's an algebra problem. To solve for v squared, the first thing I'm going to do is subtract 2.45 from both sides. That leaves me 4.9 on the left equals 0.25 v squared. Now I divide both sides by 0.25. That gives me 19.6 on the left equals v squared. And then to solve for v, I take the square root of both sides, and my answer is 4.43 meters per second for the speed of the ball when it's 0.5 meters above the ground. That is how conservation of energy can be used to solve problems. The key to this process, and remember it is a process, is that there are 3 steps. Calculate the ME at the place where H and V are known. That may not always be the highest point, so be careful. Write an expression for the mechanical energy where you want to know H or V, and then set your answer to step 1 equal to your answer to step 2, and solve for the unknown height or speed. Good luck with your conservation of energy problems.